All right. So if you could remember in the last lecture, we were studying analog to digital conversion, and we have seen the sampling theorem, the Nyquist sampling rate, and the reconstruction theorem, which was actually all covered in the famous Nyquist theorem or the sampling theorem. And we also saw its pictorial representation, guard band, all that. Other than that, I also told you some of the practical aspects that were missing uh, in the book. And so first I discussed that we need an anti-aliasing filter or a sampling filter. So first of all, to make sure that the signals are in a bandwidth, restricted to a bandwidth, so that when you are sampling at double that bandwidth, there is no aliasing, all of that. Then we were doing actually practical sampling. So, you cannot have these zero width impulses practically. You have to have a rectangular pulse. And we saw in the last lecture that the Fourier transform of that uh, sampled signal by a rectangular pulse, which could be represented by a sinc train, by a sinc Fourier series coefficient multiplied with an exponential train that we all discussed last time. And we also know that the Fourier transform of this was given as this. This we also discussed last time. So this will be, if I take its Fourier, this will be its Fourier, this multiplication will become convolution, and this train will become like this. All of this has been discussed. So if I will take its convolution, then we have also seen the fundamental rule that once you convolve the function with an impulse, so the function gets the value at the point of the impulse. So that is why the function will have this value of the impulse here, and now you will have this train. Now you can compare this train with the previous train that we had found. So this was the theoretical train, or the train when we assume that we have zero width impulses, and this is the practical train when we assume that we have rectangular pulses for sampling. And you can see basically the difference between the two is that here it is being modified by a sinc, while here it was just multiplying by a constant 1. So this means that if we will have this pictorial representation for theoretical sampling, where you can see that the spectrum is shifted after every fs, so there is a train of spectrums at every fs, uh, representing the sampling operation time becomes, train of spectrums at every fs. So this train is being modified by a sinc function. So this means this was our, if this was our fs previously, you could see that yes, fs was being repeated, but they were all of the same height. Now what has happened, that there is a envelope corresponding to a sinc. So all these replicas are there, but they are being modified with the overall sinc function. So this was all that had to be covered with respect to uh, sampling. Now we will go to the second step, and that is quantization. Now, after sampling, what has happened, that the time is discrete, time is fixed, all right, and we know it will be integral multiples of the sampling interval ts, or sampling time. But what about the amplitudes? The amplitudes could be continuous, they could take any value. But if you want to transmit any value, then you will require infinite number of bits for representing them. So, but this cannot be done because you cannot have infinite number of bits for representing a number. So what we do, we actually, after the sampling, we actually quantize. So we fix the amplitudes. So they do not become continuous, they are also discrete. This is the step of quantization. So once they are also fixed, so the signal can take one of the fixed values, and once it is fixed, you could very well see that you can represent those fixed numbers by finite number of bits, not by infinite number of bits. This is what we would do in quantization. So main focus in quantization is to quantize, is to represent the signal in fixed amplitudes rather than having continuous amplitudes. So in our course, you will just be dealing with scalar quantization. Vector quantization is not in the course. So each sample is quantized onto a finite number of levels, finite number of magnitudes. And then the second process will be that once you have these finite amplitudes, and you encode those finite amplitudes into binary representation. But that you will cover in encoding. Here you will just emphasizing on converting continuous amplitudes to finite number of fixed amplitudes or levels. So let us say the amplitude takes a set of values on the real space. So we divide them into sets, let us say n sets, and each set or each subset onto which this set has been divided is represented by a point. Here we denote this by x hat, which will represent that region or that subset. This x hat will now be called the quantized version of the continuous x. Then we will take these quantized values and we can represent them by binary bits, and that will be called coding. So let us say if we have divided our real space into n regions, so we will have n different quantized representation points or quantization levels. We will have n levels. So how many bits you will require to represent all these n levels? It will be simply log to the base n. For example, if I take 8 levels, I will just require 3 bits, because 0, 0, 0, 0, 0, 1, and then going on till 111, you can represent these 8 different values. So your signal will be totally converted into bits. So for one sample, you will now be getting log to the base 2n bits, or you can say r log to n bits per sample. Alright, we have represented it by a quantized level, representation point x hat. But what is the disadvantage? Disadvantage is that this will introduce a distortion. So first we will just concentrate on description of this distortion with respect to certain examples. So assume that I am using an 8-level quantization scheme. So these are the amplitudes from 0 to A1. Amplitude of the input signal, you will be representing this by x1 hat. From after A1 to A2 you will be representing by x2 hat. From A2 to A3 you will represent by x3 hat, and so on and so forth. These are the continuous amplitudes, and now these are the quantization levels or the discrete amplitudes which are representing those continuous values. The regions, you can see here, because you have 8 different values, so you will have 8 different regions, and all of them are described here. And for each region, if your continuous value belongs to a region, the quantization function or the quantized value will be just xi hat. So depending on which region your x falls, so the region's representation, which is given by x hat or xi hat, corresponding to the ith region, that will be xi hat. Now what will be distortion? Distortion will be the difference between the actual continuous value and its representation. So we can use different measures to represent distortion. The popular distortion measure is called the square error distortion, where again we have distortion x minus x hat, but we take its square. So we represent its square, which will give us the square error distortion. So for our case, as we know, x hat is equal to q of x. The distortion will come out to be x minus q of x, or you can say x minus x hat whole square. And this x minus x hat is the error, the distortion between the actual value and the quantized value or the quantization function. So we can represent this as another value as x tilde square, x tilde square. So x tilde is x minus x hat. Now another thing to notice is that x is the signal, incoming signal. So incoming signal, it is a signal which is random due to noise or due to itself the message signal, which might still be random. So x is random, hence q of x will also be random, and random minus random, this means x tilde will also be random. So all will be random. So you can also represent them by random variables. So you can just write x minus q of x, they're all random, giving us x tilde, which is also random. So I can also find the average value of this squared distortion. So I just have to take its expectation or expectation of x tilde square, and I will get the average square error distortion, or mean square error distortion. A good example. Here we say that x is an stationary Gaussian source. This we studied in chapter 5, with zero mean and power spectral density. So you can see the power spectral density extends from minus 100 Hz to plus 100 Hz, and the height is 2. Signal extends. Signal is a random process with a low pass signal from minus 100 to plus 100. So we sample it at Nyquist rate. This means you'll be sampling it at exact double the bandwidth. So its bandwidth is 100 Hz. So we'll be sampling it at 200 Hz. Then each sample is quantized using the 8-level quantizer, which is shown in figure 7.3. So we saw that figure, previous figure. So we will be quantizing it with that. The values of A1, A2, they are given here. These we have seen that they were the boundaries, and values of x1 they are also given. So we know these were the quantization level or the fixed amplitudes that were representing the different regions 1 to 8. So question is, what is the resulting distortion and what is the rate of the data coming out of the sampler? So we have seen the sampling frequency will be 200, And we have seen also that the sampled signal is a zero mean Gaussian with this power density. So if I want to find its variance, so we have seen earlier in chapter 5 that if you want to find its variance, you know, is actually the autocorrelation function with zero delay. You can also represent it as an autocorrelation with zero delay. And we have seen the autocorrelation function with zero delay is actually the power spectral density with EJ0. So just sum or integration of the area under the curve of the power spectral density will give you the autocorrelation function at 0, which is actually the variance of the Gaussian process or the process, random process. So we can, or the White's stationary process. So you just put its height is 2, going from 100 is 200, 200 to 400. So you can see the variance comes out to be 400. Now we are using an 8 level quantizer. So you know n is equal to 8. So you will require 3 bits. 2 to the power 3 is equal to 8. So you will require 3 bits to represent each sample. Sampling frequency is 200 hertz. So this means that after every second, in every seconds you will have 200 samples, and you know each sample will have 3-bit representation. If someone has any question, you can ask. 16, roll number 8, you have done. All right. So I'm muting him. Please ask a question rather than just turning on the mic, because you know this case creates a lot of noise and disturbance during the lecture. Alright, so coming back to this lecture, so you can very well see that the rate will be 600 bits per second, because you will have 200 samples per second. Alright, then each sample requires 3 bits, so you will have 600 bits per second. Alright, so you can write this as 3 bits per sample multiplied by samples per second. Samples cancels, and you get 600 bits per second. This was the rate, but you know we also need to find the distortion. So we just saw that distortion means that you need to find the average squared distortion, or average distortion, you can say average mean square distortion. Distortion means actually, you know, squares. When we say average square, this means that we are taking mean square distortion, or we can say we are taking average distortion. So distortion, which means average distortion, is just the, you know, expectation of the distortion function. This is the mean of the distortion. So you know, applying the principle from the random variables, mean value of this will be this function times the PDF of this function. So this function times the PDF of this function. So what is the PDF of this function? You can very well see here that you know x was Gaussian. All right, so x hat, this is also Gaussian, and x minus x hat, this is also Gaussian. So you have a Gaussian random variable. All right, so I express this, the function itself times its PDF. The PDF of this whole is also Gaussian, because each of them was Gaussian, and you can also see that q of x is a function of x, which is Gaussian, x is Gaussian, so you just put, you can apply the, you know, the rule, function times the PDF of the random variable for which this function is a function of. So you can just put it like this. Now here you can see that q of x is not one value, it is different 8 different values. So I will put those 8 different values and sum up over all those different regions or different values. and this will be giving me the distortion. So he has put that qx values, so they will be going from x1 with these limits, then we have xi hat, second region, third region, for up till the seventh region and eighth region. So these two are different because minus infinity to a1 and a7 to infinity, these are the two end regions. Rest of the regions are in between, there from ai minus 1 to ai, the in between regions will be like the rest of the functions are the same. This will be x1 x8, this will be the in between values from x to xi. So here we already know that fx, which is a PDF of x, it was a Gaussian random variable, mean was 0, and the variance comes out to be 400. So you can represent its PDF by a Gaussian random variable of 0 mean and 400 variance. So this will be 2 pi 400 e minus 2 sigma square, which is 800. This will be its PDF. So if you solve this integral, you get a value of 33.38, and he has actually missed a lot of steps in solving this integral. So I will be explaining how you will solve this integral in a while, but let us, for the sake of simplicity, just assume that, let us say, we have solved this integral and we have seen this q function, and d comes out to be 33.38. Now if d is this, so what would have been the distortion if we haven't used this representation in these 8 different levels? So in that case, you can see that the worst case scenario would be if I use 0 bit per source output. So I do not use any output, any representation. For by source. So in that case, let us say I just set the output to 0. So the distortion would be the maximum, that will come out to be x minus x hat, which is 0 now. Ex square is 400 square, 400 sigma square we have already seen is 400. So distortion is 400. Now our distortion is 33.8. So actually, if you take the ratio of 400 to 33.8, this means we have reduced it by a factor of 11.98 by using our 8 levels of 3 bit per source representation. You can take its log, 10 log, comes out to be 10.78 dBs. So distortion has been reduced by using a 8 level quantizer. Alright, before we go to the other measure, I will just try to explain this solution of this equation in a while, so that you are well versed of its solution. So you could see distortion was given as follows. There were various 8 terms, so we just concentrate in the first term. If you will understand its solution, you will be able to solve also other integrals. It was x minus x1 of the first term from minus infinity. This was the regional signal, and this was a distortion, and this was its PDF, giving me the total distortion. Also other regions are there. So I open this case, it's comes out to be like this. Multiplying by fx, I get these terms. So, fx is a Gaussian, so x squared this thing, this becomes one term. X into Gaussian, this will become just a Gaussian. So I have three different terms, all right, with integral limits the same. So first of all, I will try to explain how to solve this integral. Maybe many of you have studied this in your probability course, so that would be a revision. Otherwise, it's something we use heavily in the next chapters. So we've defined the Q function, the famous one which I think you have studied in your previous course. Let us ask someone. हाँ जी, सलमान जमील, can you hear me? सलमान जमील.
जी सर. जी सर.
अच्छा, आप लोगों ने Q function पढ़ा है? The area under the curve of a Gaussian random variable.
नहीं सर. सर इसमें ना हमने इसकी सिर्फ CDF ही देखी थी, PDF के इंटीग्रल्स नहीं सॉल्व किए थे. गॉसियन रैंडम इसके CDF टेबल से ज्यादा सॉल्व किया था, तो इंटीग्रल इस टाइप के हमने सॉल्व नहीं किए ज्यादा.
अच्छा, अच्छा, नहीं तो मैं ये CDF ही हो जाएगी ना. जब आप PDF का इंटीग्रल लेंगे तो CDF ही बन जाएगी. तो मैं कह रहा था कि गॉसियन का आपने ऐसा कोई Q फंक्शन है, एक्चुअली वो एक आप समझे कि मैथमेटिकल फंक्शन होता है. वैसे तो आपको मेरे ख्याल से CDF निकालना आती होगी ना, Q उसकी गॉसियन की इंटीग्रेट ही करना है गॉसियन.
सर CDF टेबल दिया होता था. CDF मतलब टेबल दिए होते थे उसके, तो जो बुक थी उसमें स्पेसिफिकली लिखा था कि इंटीग्रल को एनालिटिकली सॉल्व करना मुश्किल है, तो इसके लिए CDF टेबल गिवन होगा. तो ये इंटीग्रल्स हमने सॉल्व नहीं किए थे प्रोबेबिलिटी में, टेबल ही गिवन होता था.
तो जो टेबल है ना वही तो Q फंक्शन है.
सही.
चलो खैर, आज आपको दिखा देता. ठीक, ओके, मैं समझ गया. थैंक यू फॉर द फीडबैक. ऑलराइट, सो as your friend was saying that you are given a table. Actually, that table is taken out from this Q function. How? Now remember, what is it? This is the standard Gaussian random variable with zero mean and unit variance. Sigma square is 1. All right. That is why this is like this. I am just integrating it from a to infinity. So this is, I know this is not the exact definition of CDF, because if it is fine. CDF up till some point for a Gaussian random variable, that will be from minus infinity to that point. All right. But this Q function is actually defined from Q function of any point A is actually the area under the curve of a standard Gaussian random variable from that point to infinity. हाँ सलमान साहब, आपको फर्क समझ आ गया यहाँ पे CDF का और Q फंक्शन का?
जी सर, क्लियर है.
चलें, ठीक है. This is the Q function. So Q function is also the area under the curve, okay, of standard Gaussian, and that all I have written here, and it is going from A up to infinity. Little bit different, but this is used in industry a lot. So let us just now we try to solve this one. Also, this is a definition of the Q function. So we try to solve this function, okay, and you can see it looks like it is a CDF, but we will be solving this in terms of the Q function. So Q function is actually given to a communication engineer. So we just want to map it to a Q function, so that then all of the bit errors, even up in 2G, 3G, 4G, even all types of communications, AWG, they're all the errors, they're all given in terms of the Q function. So Q function is a very fundamental and important function. So mind you, this example might not be covered by Dr. Tahir in this detail. He will be giving Q function mostly in next chapter, but I thought that it is better that you get an idea here and also see the relevant mathematical skills that are required to solve a function with the Q function, so that we are well versed when we go to the next important chapter of digital modulation and all that. All this integral, so I will try to mold this integral into the Q function, so that I get this integral output in terms of these Q functions. The Q function, as your friend said, that see it is difficult to solve, and you have those CDFs. So similarly, this is just like area under the curve, just like CDF. So these Q functions are already tabulated for every other value. You just have to put the various integrals in their forms, and then you can find the values of these Q's from the Q table. Right, I had this integral, so how can I solve this with respect to the Q function? So again, I will use the famous substitution. Now you are well versed with substitution, even you have studied this in your EMT and all that. So I say that my x, why I'm substituting, so that I can mold this into the standard Gaussian random variable. So I say that my new variable is x dash, which is x over under root 400. So this means that your x will come out to be x dash 400, or you can see that your x square will come out to be x dash into 400. So this will come out to be x dash into 400, and you can see 400 will cancel with 800, you will get 2, so you will get x dash square over 2. This is the same thing I have done here, x dash square over 2, you will get 400 will cancel with 800, and again this means that you will get the standard e minus x square over 2 form. In the limits, this was going up to a1, so x dash will go to a1 over 400 under root. This will become like this. And with respect to d, previously you had dx, so your dx dash will be dx over 400. So dx will be replaced by under root 400 into dx dash, under root 400 dx dash, 400 dash, 400 will cancel with this 400. And now you have the famous standard Gaussian random variable with change of substitution of x dash, and limits are slightly changed. Now here, this is the area in the curve from minus infinity to this. This is, the CDF. But we want to write this in terms of the Q function. The Q function gives us from a to infinity. Alright, Q function will be starting from a. Q of a1 over 400 will be the value in the curve from a1 over 400 up till infinity. But I want this area in the curve. It's very simple. The total area in the curve is 1. Just 1 minus this much area, you will get the area from here to here. So we will just put this at 1 minus Q of a1 over 400 and the root, where just to explain you that a over 400 means that you are starting the curve, area in the curve from a1 over 400 to infinity, the standard Gaussian random variable PDFs, and this will give you the area under the curve for this expression. हाँ जी सलमान साहब, समझ आ गया आपको मैंने कैसे चक्कर चलाया?
जी सर, ये तो वही है ना, आप नॉर्मल रैंडम वेरिएबल को स्टैंडर्ड में कन्वर्ट करके उसकी सीडीएफ यूज कर रहे हैं, ये किया हुआ है, लेकिन इसको हम
बस ये सीडीएफ को थोड़ा सा भूल के ना, यहाँ पे हर चीज को आपने क्यू फंक्शन हर जगह आपने क्यू की टर्म्स में लिखना है।
Q1 माइनस सीडीएफ है, क्यू फंक्शन 1 माइनस सीडीएफ है ना बेसिकली।
हाँ, क्यू फंक्शन जो है वो 1 माइनस नहीं सीडीएफ हो गया ना, 1 माइनस क्यू फंक्शन इस केस में, ठीक है ना? सीडीएफ यहाँ पे 1 माइनस क्यू हो गया ना इस केस में।
हाँ ठीक है, सही है जी सर,
मगर अगर
बस वो किया किसी और,
इसका मतलब आपने क्यू फंक्शन पढ़ा हुआ है?
मतलब कि टर्म्स कुछ और यूज की थी, क्यू फंक्शन एग्जैक्टली हमें नहीं बताया था ये क्यू फंक्शन होता है, हमें बस ये पता था ये सीडीएफ है और उसको स्टैंडर्ड नॉर्मल रैंडम वेरिएबल को स्टैंडर्ड में कन्वर्ट करके कैसे फाइंड करते हैं, तो इसी तरह का था।
ठीक है, और इसमें ये ख्याल रखें a1 असल में नेगेटिव था, ठीक है? अगर a1 पॉजिटिव होता तो ये माइनस इन्फिनिटी से यहाँ तक का एरिया हमें चाहिए होता, तो वो भी सिंपल था, पहले आप वही q को लिख देते एक ही टर्म्स में, सारा का सारा वो आ जाता आपके पास, और फिर वही 1 माइनस कर देंगे तो फिर ये एरिया आ जाएगा। वो तो आप अपने हिसाब से कर सकते हैं, जिस तरह भी उसकी वैल्यू हो, बस ये आए टोटल एरिया इन द कर्व इज 1, तो बाकी जो माइनस सब्ट्रैक्ट कर दें। अच्छा, ये वाली एक्सप्रेशन आपने सॉल्व की है इस तरह की सलमान साहब? क्योंकि अगर आप देखें ना हमारे पास जो ओवर एक्सप्रेशन बन रही हैं, सो यू कैन सी वी हैव 3 expressions 1, 2 and 3. So I would like to explain all of them. They are very 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 important, especially for communication engineers, to how to solve these Gaussian functions, integrals, along with their x powers. Have you ever solved these types of integrals in your previous courses?
सर वो इस तरह के ना हमने इंटीग्रल्स तो मतलब कि शायद आप करेंगे तो किया हो, लेकिन असल में हम इस तरह के इंटीग्रल सॉल्व नहीं करते थे, हमें रैंडम वेरिएबल दिया होता था, उसकी वो वेरिएंस और मीन गिवन होता था, तो उसको हम स्टैंडर्डाइज करके उसकी सीडीएफ फाइंड कर लेते थे।
नहीं,
तो
ये
ये
कुछ
किया
और
था
चीज, ये इसमें
हमने,
भी
ये भी
आपने
किया हुआ फिर।
आगे, हाँ पहले ये देखें, इसमें चक्कर चलाया ना, गॉसियन के साथ ये एक्स है। प्रॉब्लम ये है कि गॉसियन का इंटीग्रल तो निकलने से रहा, फिर हमें चक्कर चलाना पड़ता। एंड दी आर द फेमस tools that must be well versed for, especially for communication engineers of signal processing domain. I told you communication engineers, there are two types. One are the electronics type, which go with circuits and electromagnetics, and other that go with signal processing. So this term, how can I solve this integral? So I apply a trick. I know the derivative of this term is this thing. All right, just its derivative. This expression is the same. Derivative of this will be minus 2x over 800. So I can write integral of this thing will be equal to integral of this whole. And you can now compare that this whole is this. Alright, I will just multiply with minus and take care of the constants. I can just put the whole integral as equal to this thing. This is the main trick. Just applying this trick here. So actually I had this much expression. I multiplied by minus and minus both the sides, so that originally it was plus. And I divide by 800, multiply by 800, so that everything is balanced. But I know that this integral is actually equal to this thing. Alright. And once it's this thing, I just put the limits. Here also one important thing is that limit of e infinity square. So infinity square will be infinity square, but e minus this will tend towards 0. So will go towards 0, and hence the second expression is also solved. Here do not need any q function, you just get the answer. Alright, third expression of this x square. And is तरह की फिर, yes, you have not solved these expression also, so you can see the trick here also. Again, I will apply the trick along with integration by parts. So I will first of all say, all right, this is x square, but I will break it this into x. All right. This part I already know I can solve this as in the in the previous, as I told you, in the second expression. And this with this I can use the famous integration by parts. So I do this, multiply and divide by these things. Again, to apply my trick here. So minus 2 comes here, this comes here, 800 comes here, all of this goes out. And again, this expression, यहाँ पे dx में लिखना भूल गए, यहाँ पे आप dx डाल दीजिएगा. Hence this expression is also the same expression that we just saw earlier. So I apply my integration by parts. So this as it is, integration of this, we already saw it is actually the same exponential with these limits. Limits are there. So this is second term. Then derivative of the first, and again integral of this is this, and then again its integration. So we have solved this earlier, so this will come out to be like this with all the constants here, and this is again can very easily be converted to a a normal Gaussian standard form, as we have just seen earlier, by multiplying and dividing by appropriate constants. So this will come out to be like this, and hence this expression is also solved. All right. So I know that this is very long. We have 8 different levels or 8 different very huge integration, but we cannot give this huge in exam. But part of this could be given in the exam. But I have given you the basis of solving any of these different 8 parts. So this was one example where you're finding a distortion when we knew that the signal itself was a Gaussian signal was a stationary Gaussian process with all that explanation that we saw earlier. Now another measure that is used is which is actually more important. You can say it is more industrial oriented than this distortion or this mean. It is a normalized version of the quantization noise. Here we normalize the signal with respect to the power of the original signal. Let's try to understand this thing also. So first what we do, we define the important thing SQNR, which is called the signal to quantization noise ratio. All right. So this will be the signal power. A signal power we just saw in the example also in chapter 5, that signal power is what? It is the autocorrelation function at zero delay. All right, or it is the variance. You can write it variance, autocorrelation is 0, or you can say the area under the PSD, that gives you the power of the PSD, the power spectrum density here. You find the area under the curve, you will get the power. So all of them are similar. This gives us the power of the signal. Then previously we had SNR, signal power over noise power. So here we have signal power over, but noise is quantized. All right, because the the noise, what is the noise now? Noise is actually quantized in a way because you have the signal minus its quantized value, because now you're working with quantized value. So that difference is the distortion. So we use distortion for x minus qx square, and then we take its mean. So this will give me, this is not the actual noise. अब actual noise नहीं है जो आपने अपनी कौन सी rectified Gaussian noise डाली थी, जो भी channel के effects है. This is a quantization noise, a noise that has come about by the introduction of quantization. Right? So we just saw this earlier. This is its mean, same thing. This is the ratio of the signal power over the quantization noise power. So quantization noise power, okay, how can we find this? So if you want to see the exact formula for finding the quantization noise power, then you have to take it as a power signal. So you first find its mean and then you find its power. The same formula for power, right? What is the power signal? It is going from infinity to infinity, so it will have, and you find its mean and then you find its power. And the signal power, the same thing, you have the signal. So you know why these e's are there. Previously if they were deterministic, then these e's were not there, but once these are random, so you have to take their e's or their expectations, so that, all right, you get a deterministic function in terms of t, and then you can integrate it. All right, so this gives us the formula for finding the power of the signal as well as the quantization noise power. So the ratio is again the same, px over px. इसको टेल्डा लिखा है, साफ नज़र नहीं आ रहा, बट इस टेल्डा पे आपने देखा था कि वो x माइनस क्यू एक्स को हमने टेल्डा कहा था, तो फिर उसके बाद इसका मीन हो जाएगा, उसका स्क्वायर होगा, मीन होगा, तो फिर उसको उसने पी एक्स ऑफ टेल्डा लिखा हुआ. नोटेशन आप यूज़ कर लें जो बेहतर है, बुकी की यूज़ करें ताकि एंड प्रॉब्लम्स भी कवर हो जाएं, एग्जाम भी कवर हो जाए. And you can see here that if xt is stationary, then in that case SQ and R will come out to be like this. So you don't have to take these integrations, but for that it has to be stationary. Then you can use a simplified, otherwise you have to use these full integrals to solve them. X is a random variable representing xt point. So you can see the difference here. Here this was the random variable, while here this was actually the x of t. This was a random process. So in case of stationary, we have learned in stationary processes that their means are constant as well as their autocorrelations. They are dependent only on the difference. So with all that consideration, you can very well see that for stationary processes you will be getting this equation, but if it is not stationary, then in general this will also work for stationary processes. You can very well see, no problem. So but for stationary you can see that this will actually come outside the integral, and this will totally tend to be t, dt cancels, this becomes 1, so it will come out to be the same expression. This is general expression, you can always use this, but no need to go into this complicated form once you already know that it is a stationary process. So in the previous example it says that you have to find the SQ and R. So signal power we just saw, we find the area under the curve, that comes out to be 400. Noise power, what is noise power? We just saw this is a noise power, average of the mean square distortion. And what was that? Here we were doing the same thing, this was the same thing, we were finding the same thing, this is the same thing. You already found distortion was the average मतलब एवरेज मीन स्क्वायर डिस्टॉर्शन कह लें या जो भी एवरेज डिस्टॉर्शन को हमने डिस्टॉर्शन कहा था. So this we have already found, and it comes out to be that same value, 33 point something I think this value. And so 11.98 and then 10 log of 11 comes out to be 10.78. So by signal to quantization noise is 10.78. Other could be what type of quantization you could use. One is uniform quantization, in which you have regions, as we just saw in example 7, the figure 7.3 in the previous examples. All regions are of equal length except the end regions, which are very large length because they have to cover the whole range. And the interval we denoted by tilde, each interval, वो जो बीच के intervals हैं उनको आप ये tilde से donate कर सकते हैं. And the same equation, वही ऊपर की equation है, but you can also write it like this. This will be the two end ones and these will be the in between ones. वो देखें इसमें सारे के सारे in terms of A1 you can write them, but they are all going ahead with a tilde interval. So हर interval tilde है, so you can represent this also in terms of tilde. So the D function could be represented in terms of A1 and tilde. So you can differentiate this with A1 and tilde to get the best values of your optimal quantizer, so that you can minimize. इसका पर लंबा चौड़ा प्रोसेस वो हमारे कोर्स में भी नहीं है. अभी ये इसका पूरा डिफरेंशियल ले अब A1 के हिसाब से और ये A1 और टिल्डा के हिसाब से, फिर उसको 0 के बराबर रखें, फिर उसको करें ऑप्टिमाइज करें, वो हमने नहीं करना, वैसे बताने के लिए था आपको एक दफ़ा. So this has already been done for Gaussian random variable, assuming that your signal x is a zero mean Gaussian random, zero mean year to point. So this has been already tabulated, so you can see this table. You don't have to find it. The table values are all given. That so for, let us say, if I have 8 number of levels, what should be the tilde value and what will be the mean square error, and so on and so forth. Other process which is mostly industrially used is non-uniform quantization. We say no, it is not necessary that you have intervals of equal length. You could have different matlab, different lengths. Every interval could have different lengths. In that case, distortion will become like this. Again, the same function, but here we don't have those uh, fix tildes or tilde plus one tilde, they are not there. You are just getting those x values. आप देख लें यहाँ पे फ़र्क समझ आ रहा आप x से पहले भी जमा यहाँ पे देखें ना सारे के सारे they were represented in terms of tildes because tilde was fixed. Now there is no tilde is not fixed, or it could be anything. So we are just doing the same process x minus x1 hat and the same thing that we saw earlier, square and all that. Now how can I optimize this? Again, I can differentiate this. Here you could see that what are the variables. The variables are these boundary values and the variables are these x values. So if I differentiate them, let us say with respect to one ai, I differentiate this whole expression with respect to one boundary condition. All right. So some steps are always missing. So I have turned to my notes. So we know the famous rule, and I know you have studied this integration. Take the derivative of an integral where the limits are itself the function. So you get the function value at the limit value times the derivative of the function or derivative of the uh, limit minus the function value at the second limit times the derivative of the second. But here our forms were from ai to ai plus 1 and the differential was being taken with respect to ai. So I have this function, so I will get g of ai plus 1 times ai plus 1 with derivative of ai is 0, so this all goes 0, minus g of function at the lower limit. Alright, derivative of ai with ai will be 1, so you will just get minus g ai for this. Our case, our g of t function is g of x, which is this thing, so you will just put this value here and your g of ai will become this function with x replaced by ai. Another function will also contain if this is going from ai to ai plus 1, the previous one will be going from ai minus 1 to ai, and its derivative will come out to be first one. ai will be here, so you will get the first one, g of ai and g of ai is equal to uh, x replaced by ai, x by ai minus xi square. All the other terms will 0 because they will not contain ai in the limits, and you are differentiating with respect to the ai, not with respect to x. So after all that differentiation of the whole term, you will just get these two terms. Again, you can see I will put these two terms equal to 0. fx will cancel, assuming that the probability of ai is not 0, so fx cancels, and these two terms, this term will go on the other side of 0, so you will get this term, and you can open up the brackets, so you will be able to find the value of ai as mean of the two values that have been chosen the quantization levels. You have two consecutive quantization levels, the boundary condition will be the mean of those values. Again, many steps are missing in the book, but you can just follow my notes and you will get this proof. The boundaries of the quantized regions are the midpoints of the quantized values. So a famous result. We also highlighted. All right. And then this was with respect to AI, but what about xi hat? So again we take the same d and we this time we differentiate with respect to xi hat. Then you will see here actually xy is xi hat square. So differentiating this will 2 will come here, and you will have minus 1 into fx integral. So derivative will go inside, and the rest of the terms will remain the same. Derivative goes inside, and then this is 0. All other terms which do not contain xi hat, they will already go 0. So you will get this term. So you can open this up. One term will be 2x into fx, other term will be minus 2x into fx. One will be 2x into fx, other term will be 2xi into fx. You can take xi common. So the x term will remain here, 2 will cancel, and xi will come out to this over this. So these are the optimal values of your xi's, which are the quantization levels. So quantization value or the xi's for a region should be chosen so they are the centroid of that region. So this is the formula of the centroid, so you can just say that xi hat are the centroids of their regions. So we have two optimizations. One is with respect to the quantization level, and other is the quantization level itself. So you have two quantizations. We have to analytical solutions become quite cumbersome. So we use the usual iterative method, and so the iterative method is that short for values, and using the second criteria find those quantized values. Then from these new quantized regions, for these new quantized values, you just alternate regions, values, regions, region, values, region, this way. So I will take a break here. All right, thank you. Hello. Assalamualaikum. Sorry for the interruption. So I had an important call. I had to be attended. All right. So this goes on and on till the error between the relevant steps, first step, second step, third step, error tends towards 0. Then this means that you do not have to quantize further or choose other centroids or boundary conditions. Again, this is a long process, not in the course, and a table has been shown that give us the optimal non-uniform quantizers for again a Gaussian source of unit value. If you don't have a Gaussian source, rather you have if you don't have a standard value Gaussian source, rather you have some mean and some variance, then just change the values of the variances of the boundaries and quantized values or quantization levels by m plus sigma. सिग्मा से मल्टीप्लाई करें, m से ऐड करें, जैसे आप पढ़ते भी आए वैसे क्वेश्चन में जब चेंज आता है तो इससे चेंज करते हैं कि स्टैंडर्ड से आप किसी और जगह जाते हैं किसी और क्वेश्चन में, यू चेंज द मीन and the variance as follows. So again your AIs and XIs will be changed as follows with respect to the multiplication with the variance and the addition with the mean. and distortion factor is changed by sigma square. You can see. Let's do the same example, but now we use a non-uniform quantizer. Okay, so what is the distortion and all that? So again, you can say this is already there. We know the variance is 400, so you know power will be 400. No need to find out. Uh, but we need to find the distortion which has changed. So we know the levels. We will just use this table and uh, okay, the table is standardized, but you know our mean is 0 and sigma is 20. So we will just take the values of ai and xi from the table, and we'll be multiplying them by 20 and adding them with 0, which means nothing. So we just multiply with 20. Distortion will be multiplied by 400. All right, and how we will, which row will we choose from the table? So you can see again we are using 8 number of levels, so we'll use the table having 8 number of non-uniform levels. Non-uniform, so you will just go to this one, copy all the values of AIs, copy all the values of XIs, you know, multiply and or add if there's to be addition, and you will get your distortion. Distortion comes out to be this thing, signal power is this thing, and hence SQ&R is this, and hence you can take its log. So you will find is 14.62, which is better than the SQ&R of the uniform quantizer. So yes, non-uniform is always better than the uniform. Vector quantization is not in the course, so we will leave this part. All right. So then we have encoding. It's very simple, but I will also discuss this. Various types of encodings are used, and we see in gray code. We can discuss this in the next lecture. I will discuss that. Very simple. You can also do it by yourself. But I would like to go to the more of the industrial aspects. So waveform coding. So we need to design our coding schemes, because now we have just seen that by quantization and then by, so roughly I can just tell you what is encoding. Encoding, I have just told you that you are representing your signal by n different levels and different x hats. All right, so each value is now represented by a bit. All right, it might be 000, let us say 3 bits. First you say first amplitude is 000, second is 001, whatever. So you can see here, so these are the various quantization levels. There are various types of, you know, coding, gray coding, and then we have this NBC coding, which is natural binary coding, which is our case. Just I told you, first level yes 00, second yes 001, 10 and 11, like this. You can choose representation. So what has happened, that now for, let us say you have 16 levels, so every sample is just given by these levels, by these bits, 01 bits. So your data has been totally discretized both in amplitudes as well as in time, and this is encoded by these zeros and ones. Uh, yes, we use other also gray coding. In gray coding, we can use a different here. The main thing is that you just make sure that once you go from the first to second level, there's only one bit of change. तो देखें यहाँ से हमें हर में एक bit का change. That is why gray coding is also used like this. So various coding schemes are there. So we just saw that what is our objective. We want to sample, we want to quantize, we want to encode in such a way that once we reproduce our signal at the output, we have little distortion as much as possible. This is the main thing. Yes, so main focus is that we are able to reproduce our signals with higher fidelity. We are not interested how this signal was formed, but we are interested that we are reproduce the signal as I have my output input frequency. My signal which I am speaking to you is being digitized. You should be able to hear the same signal as I am saying on this side. Alright, so the waveform properties of the waveform will affect the design and all that. So waveform coders which are used to you know discretize our signal, they have to be robust, they can work with a variety of sources, and we will study some of the basic waveform coding methods. They are widely used in industry. First and the oldest and the most simple is PCM, pulse code modulation. And again, we'll have three sections: sampler, quantizer, and encoder. The block diagram is given, you can see in this figure. So you have a sampler, a quantizer. You can see sampler gives us x of n's, quantizer gives us xn of hats, and encoder gives us 0101 for each x hat quantized level. So assumptions are there. First of all, signal is limited to W bandwidth, and then for reconstruction you will use a bandwidth of 2W, or you can also use higher bandwidth. Signal amplitudes are all less than x of n. This may show that no signal is greater than the maximum value. Third thing, that we have a large number of quantization levels, and many levels, 8, but all those levels have to be a power of 2. They have to be some power of 2, so that you can represent them in a very good binary representation. Right? Could be 2, 4, 8, 16, 32, but largely 256 greater values are used for representing number of quantization levels. So as I told you, we have an book says it is a pre-sampling filter. You can give it any name. First of all, we will have a pre-sampling filter that make sure the signal is restricted to W bandwidth. Then we will sample it Nyquist rate. Nyquist rate we will sampling at 2W. Greater than, if you want to put some guard band as we discussed, alright, then you can sample it at higher rate. Whatever, you have to sample it at Nyquist rate or some at higher rate. Then your sample values, they will now enter a quantizer. So scalar, we are not using vector. Vector is not at the course. Scalar quantizer. So scalar quantizer could be a uniform or it could be a non-uniform. As you just discussed, there are two types, non-uniform. And the type of quantizer, uniform or non-uniform, is dependent on the characteristics of the source. Or whatever the signal that we are getting, you will determine our quantizer based on the signal properties. Alright. So again, output of every quantizer is encoded. We have already seen. So we have n levels. So we have n levels, but n level every can be represented by 2 to the power 3 levels. So 3 bits will be, or V bits will be enough to represent every level. As we have just seen, for 8 levels we just need 3 bits. 2 to the power 3 is equal to 8. So uniform PCM, where most of the regions are of fixed, except the end ones, all the other regions are of fixed length. So there, first of all, the total signal is between minus x max to plus x max. Is also made sure. And so once we know that the signal is fixed and these are the regions, so I can very well divide this whole region from minus x to plus, which is of a width of 2x max divided by n. So in the previous case, actually, if you remember, we were all right. So in uniform PCM, we divide the whole region by divide by n. So we know the maximum signal is x max, the minimum is minus 2x, total range will be 2x max. We divide the total range. Here you can see we don't have those n regions of different length. All of them are the same length because we have restricted our signal to x max. So n is equal to 2 to the power v. This 2 comes in the denominator, so it will become 2 v minus 1, or you can also write 2x over 2v. Same representations. This is my length of my region. All right. So again, what is the error, distortion error? We know is x minus q of x, and we will be seeing that this x tilde in this case, where tilde is fixed, and q of x is the quantized value, while x is a random variable. So in this case, this x tilde will come out to be a uniform random variable. First of all, it will be random variable from minus delta to plus delta over 2. Okay, and ordinary PCM, actually the n is very high and signal amplitude are small. Okay, so you could very well realize that signal values are small and n is very high. So this tilde PDF will just look like a constant function. Will this x tilde will here will look like a uniform random variable, all right, on this region. Okay, and I've told you why this would happen, because of these assumptions which are written here. Signal levels are high and levels are high and the amplitudes are very small, so it looks as if that in this small tilde the signal is uniformly distributed. So my probability of this tilde is 1 over tilde of this x of tilde is 1 over delta, where the x random variable goes from minus delta over 2 to plus delta over 2. Alright, so this is the representation of my distortion error. Now, alright, the time is up. I am sorry, in this lecture I was having a brief duration of sleeps. That was I was quiet for a while. Alright, if anyone has any question, you can ask. The time is up. I'll stop. We'll start with the next lecture from this point onwards. I will stop the recording.